Okay, so this is what we are doing today. All right. We have our slide here. Oops, the wrong slide. There we go. All right. So we have our slide here about what we're doing today. And we got somebody else coming in to visit. All right. Okay. All right. So today we are taking notes. And I know that is probably not the most exciting thing that we ever do in this class, but I do have good news. These are the very last set of notes that we will take in comp science this year. So this is it. This is the last of our information. And it's about objects that are falling. And so that's what we will be talking about today. You've got a sheet that looks like this for your notes. Let's see here. Um, right here. So you want to have let me make sure that I am showing you the right thing here, and that this is the notes and not the homework, because I want to talk about that too. But I think I am showing you these notes right now, and let me make sure that I am. Yeah, I am. Okay. All right. So this is the only thing that you really need to have today with you in front of you is this document right here that's called Notes on Falling Objects. And I am going to go through a PowerPoint with you. I've also got a couple of videos to show you at some different times, and a little demonstration. But you are going to be answering questions and filling in the blanks on the sheet while we go along. And there are, I think this is 3 pages. Let's see, it's 1, 2, yes, 3 pages. Okay, so then I want to also talk to you about our homework. So let's go back to our daily slide for a moment and look at our what we have going on and do for this week, because I know you guys definitely care about what it is you need to turn in today. All right, we got Toby and Asher joining us. All right. Hi, Toby. Hi, Asher. Okay. All right. So I should be sharing with you right now our slide. And again, we're taking notes on falling objects, and you have that handy, which you see right here in blue. Materials needed now are your notes on falling objects, that worksheet. That's the only thing you need today. These notes you are going to turn in for a grade. They will be due on Friday by 2 p.m. Then on Thursday, which is our next class this week, we are going to be building launchers. And when we build these launchers, let me show you what the one is that that looks like. The one that we're going to build on Thursday looks like this one. I am going to be building this with you on Thursday. So I put a document on Edsby for the materials that you would need if you would like to build this with us. Now, why would you want to build this? This is a catapult, by the way, made out of a mousetrap and a couple of, you can't quite see them, big pink erasers and a plastic spoon and a couple of popsicle sticks. So we're going to be building this together in class on Thursday. This is optional. You do not have to build this. I'm also going to post a document of some other things that you can, like a list of other launchers you can build, because you don't have to build this one. If you want to build a launcher, you can use other materials as well. Then when we are going to use this is, next Tuesday, a week from today, we're going to do a lab, our last actual lab, and it's going to be a marshmallow catapult lab. and you can use your launcher for that. If you choose to not build a launcher, you can watch me do the lab, and you're still going to be participating in filling out your sheet, but you don't have to actually build a launcher and use the launcher. But it's going to be a lot more fun if you do. And then if you do, we're also going to be using this launcher in our physics Olympics. So on Thursday the 28th, which is the day before the last day of school, we're going to have an Olympic event. It's for extra credit, so it's optional if you want to participate, but participating will give you extra credit in the class. You might want that. And this is one of the events. We're going to play Angry Birds using our launchers. And again, it doesn't have to be this exact launcher, but if you want to build this really cool launcher, look at the materials list and join me in class on Thursday, live on Zoom or on YouTube later on, and we'll build this together. This again is optional, and that is what we are doing on class and in class on Thursday, is building this launcher. So giving you a little hint that Thursday's class may not be necessary for you unless you want to build a launcher, but we are going to be doing a lab with this, and that lab will be not optional, will be required, and that's a week from today. All right, so that's our launcher, and let's go back to our homework. So the homework that you're going to be doing today, there's two documents on EDSB. One is the directions. And I think you're looking at the directions right now. I'm just not currently. They are buried behind everything else. All right. Well, hopefully you can see these directions. I just can't right now. You are going to be looking at here it is, the video game Angry Birds. And you can play it for free on your computer or tablet or phone. Doesn't cost anything. And if you don't want to play it, I suppose you don't have to play it, but it's more fun to play it. And then you're going to write, yes, you do have to write, strategies for me, how to be successful at this video game using Newton's laws. So there are actually 5 things that you will be showing me a strategy for. So far, you only know of Newton's 3 laws. Newton's first law of inertia, second law of acceleration, and third law, action and reaction. But today we're going to learn, and you actually do already know this law, you just don't know it as Newton's law, but it is the universal law of gravitation. So it's about gravity. That's one of Newton's laws as well, and you're going to give me a strategy using gravity in this game, and projectile motion, which has to do with gravity. And both of these 2 things we're going to learn about today. All right, there is a rubric that explains how I will grade this. And that's also posted for you, and it's right here. So you can see what you need to do to get an A. It's worth 25 points. You can see here that the bottom, 23 to 25 points is an A. And for each one, you have a law that you need to explain. So notice, to get 5 points for each law, you need to do this. Law, let's see, somebody's. Okay. All right. So you want to, the law is exemplified as a strategy of the game. The use of the law is clear and correct. So, for example, you may say something like, in Angry Birds, according to the second law, you have to pull back further on the slingshot to give it more force to make the bird accelerate. That would be an example of the second law. In order to get full points for it, you do need to say, this is the second law, and make sure that it's clear that your example is about that particular law. And if you've never played Angry Birds, I just downloaded it on my tablet because you do have there's a Adobe Flash Player that you need to have on your computer, and for some reason I mine was blocked. But this is Angry Birds 2. I don't care which Angry Birds game you play. You can play any of them. This one is the second one, something like Escape to Rio. And you might know that you have to pull back on the slingshot and release. Do knock over. Okay. So that's what you guys are going to be doing. All right. So hopefully you have access to be able to play that game and you'll know the strategy. If you need any help on that or more clarification, please feel free to message me on Edsby. Come see me during the office hours, and I'll be sure to help you. Okay. Trevor, you don't have a phone? Maybe you have a tablet, or you can also play it on your computer too. So if you need an alternative assignment because for some reason you cannot play Angry Birds for any reason, get a hold of me and I will give you another option. Okay. Otherwise that is due Friday, 2 o'clock. Okay. So, all right, let's, now we're going to, go ahead and get to our notes. I am going to show the videos a little bit later on versus in the beginning here so that we get everything we need to, for you to be successful. All right, so you have in front of you the notes on falling objects. And this is where we are going to put our answers today. And this is what you're going to turn in on Friday by 2 o'clock. I gave you an extra couple hours. Okay, so, all right, we are going to take a look at this PowerPoint. And I've posted this PowerPoint on Edsby for you just in case you want to go back and look at it or what have you. I am going to try to do this as a slideshow, and we're going to see how that goes. Because your animations will play here, but I just don't know if I can see your chat, so maybe I still can. Oh, sure I can. All right, so we are doing notes on falling objects. So some of our topics today are, went ahead, projectile motion and universal law of gravitation. So we all know that when objects fall down to the earth, or I'm sorry, we all know that when objects are dropped, they fall, right? But why? Why do objects fall? Why is it that when I drop a hammer, which I'm going to do right now, onto cat bed so it won't be so loud, it falls to the ground. I'm going to do that for you later when I drop a feather and a hammer at the same time, and we're going to predict which one will hit the ground first. All right. So my questions to you guys then right now is, is this force of gravity, is it everywhere, or is it only in some places? Anybody remember I'm giving out some dojo. If anybody needs some dojo points, you might know what that is for. Mr. Wolford has told you. Yeah, John, is this a force of gravity? Is it everywhere or just in some places?
Well, it's in everything that has mass.
Okay, right. Everything that has mass does get pulled by the force of gravity as long as it is in some vicinity of another object. Yes. Now, does anybody know if, dojo here, does anybody know if this gravitational force is constant? Does every object experience the same amount of force as every other object? What do you think? There we go. Anyone? Bryson? Trevor? I think Bryson still had his hand up from before. Yes, Trevor. What do you think? Is the force of gravity constant for every object?
Um, Probably not.
Probably not. You
I
are
don't.
right. It is
Oh,
not constant for every object. It depends on an object's mass and its distance. So let's talk a little bit about the gravitational force here. Okay, so we have learned in the past when we were talking about space, we did learn that gravity does exist in space and that it's dependent on two things. It is dependent upon the mass of the objects and also on the distance between them. So I don't know if you guys realize that this law is actually one of Newton's laws of motion. So this is Newton's fourth law of motion, and it's called the law of universal gravitation. So yes, gravity is everywhere, it's universal, but not all objects experience the same amount of force. So the definition of this law states that all objects exert a force on all other objects that's directly proportional to mass and inversely proportional to the distance between the objects. Now, what does that mean? It's a little scientific there. There's a couple of words in there that you might be less familiar with, and I wanted to point them out. That's directly proportional and inversely proportional. So these are mathematical terms. So does anybody know what it means to be directly proportional? Anyone? If something is directly proportional to something else, then it means that when one of these properties increases, the other property increases. If it decreases, then it decreases. So it means that it is directly proportional, that it has a direct relationship that is equal to. So if we double or increase, I should say, the mass. Not necessarily if we double the mass, we double the gravitational force. That's not exactly that direct relationship. But if we increase the mass, we increase the force of gravity acting on it. That's what it means to be directly proportional. And if we decrease the mass, then we decrease gravity. Inversely proportional means the opposite. So it's flipped. So as one increases, the other decreases. So distance is inversely proportionate to gravity. So as distance between objects increases, gravity, the force of gravity between them decreases. As you get the objects closer together, as the distance decreases, then gravity increases. And these illustrations here can show you that. So you can see in the illustration here on the left that the greatest force of attraction is between these two larger objects that are closer together. And looking at, and I think you needed to fill that in on your notes. Okay, so quick question. All objects in the universe are attracted to each other by the force of which one of these? Anyone? All right. By the force of gravity. All objects in the universe are attracted to each other by the force of gravity. That is the definition of the law of universal gravitation. And I wanted to remind you about laws in science. Remember that a law, a scientific law, describes something that happens in a certain way, in a certain situation. Theories, scientific theories, explain the hows and the whys of the law. So whereas Newton came up with this law of universal gravitation, Sir Isaac Newton, I'm sorry, Albert Einstein came up with the theory of gravity. And the theory of gravity explains the hows and whys of gravity and how, why it acts the way it does. That theory, by the way, has a name too, and that's Einstein's theory of relativity. You've maybe heard of it. We're not going to talk about it today, but we are going to talk a lot about Newton's law of gravity here. So remember, according to Newton's law of universal gravitation, the gravitational force increases with mass, but decreases with distance. So this is a important concept to think about today when we talk about how things fall. Okay, so here's a question for you to see how you are understanding this law. So if you have 4 pairs of objects that have these following masses, if the objects in each of these are the same distance apart, which one has the largest force of gravity? Is it between the 1 kilogram and 1 kilogram mass? Is it between the 1 kilogram and 2 kilograms? Between 2 and 1, or between 2 and 2? Remember, if they're the same distance apart. What do you think, John?
I think it is 2 kilograms and 2 kilograms.
Yeah, why?
Because they're the same distance as each other, as all the other masses, and plus they have a greater mass.
Yeah, exactly. So they're the same distance apart, but they are the ones that have the largest mass between them. And so they have the most attraction between them. Okay, excellent. All right, so this question I think is on your notes. Which one of the following pairs would have the greatest gravity? So same type of question. Do you think a mouse and an ant that are 1 inch away? So now we're figuring in distance here. A house in Florida, which would be at sea level, and the Earth, or a house on top of Mount Everest and the Earth, or an elephant and a feather that are 1 mile apart from each other. Which of these do you think would have the greatest gravitational attraction between them? Bryson.
I'm thinking D.
You're thinking D, an elephant and a feather?
Yeah.
Well, the only thing about the elephant and the feather here is, so an elephant has a large mass, right? So remember that gravity is dependent on mass and distance. So the most gravitational attraction is going to be with the objects that have the most mass that are the closest together. So which of these 4 have the most mass and are closest together? Because elephant's got a lot of mass, but the feather doesn't. And does an elephant have more mass than a house? Probably not. So I would think the houses have the most mass. Now think about which ones have the most mass and are the closest together at the same time. Do you want to try again, Bryson? I did give you points anyway, but I can do it again. So it's not D. You in? So we've kind of established, I think, that the house, the 2 houses in B and C have the most mass. They're more massive than a mouse, an ant, a feather, or an elephant. So it's going to be B or C for mass. Now, which one is closer? Which objects are closer to one another? The house in Florida at sea level and the Earth, or the house and the Earth, but the house is on Mount Everest. So it's at the top of the mountain instead of on sea level. What do you think, John?
I think it's going to be B because first, if you're on the top of Mount Everest, you're way farther from the center of the Earth. And when you're on sea level, you're a lot closer.
Yes, exactly. So, you know, given that the houses, you might even say, well, which house is bigger? It really wouldn't even matter, even if the house on Mount Everest had more mass than the house in Florida. The fact that it's so much closer to the earth at sea level would give that house, or I should say, there would be more gravitational attraction between the house in Florida and the earth because it's biggest and has the closest distance. So B and C may have the same masses, but they're closer together. B is closer than C. All right, good. So hopefully you answered that on your notes. And then this is just another illustration showing that. All right, so now that we've kind of established what the universal law of gravitation says, that it depends on mass and distance, the force of gravity, is the force of gravity the same for all objects? Which was my question I had at the beginning. And hopefully you can now say, no, it is not. All objects do have some force of gravity on them. So all objects do experience a force of gravity, but they don't all experience the same amount of force because the amount of force depends on the mass. So more massive objects are being pulled to the earth with more gravitational force than objects with less mass. And if you think about when an object is pulling mass down, when gravity is pulling on an object's mass, what do we call that property of the object? It's not mass, but an object's what? When gravity is acting on the mass, we call that an object's weight. An object's weight. And we know that not all objects have the same weight, right? So think about that. Because not all objects have the same mass, they don't all have the same weight. And weight is a measure of how much gravity is pulling on an object. Okay, so now that we've established that, I want to ask you the big question here. And I want you to make a prediction. You're going to make this prediction on your sheet. So let's say that you have an elephant and a feather, and they're on top of a tall building. And don't call animal control on me because I'm not really going to do this. But if we were to drop an elephant and a feather off of a tall building and we drop them at the same time, which one would fall faster and which one would hit the ground first? Okay, so make your prediction. And if anyone would like to share that prediction, which I hope you will, I'm going to ask you to raise your hand. So if you think that the feather will fall fastest and hit the ground first before the elephant, raise your hand. Is anybody raising their hands? Let me look at you guys on gallery view here. Trevor thinks that the feather will hit first. Okay. And that looks like the only one.
Oh, I meant to say the elephant.
Oh, the elephant. Okay.
Yeah.
So raise your hand if you think the elephant will hit the ground first. Nate and Trevor, that's it? What about the rest of you? You don't think the elephant will hit the ground first?
Bryson says so too.
Oh, yep. I see Bryson also, but that's it. There's John. Okay. How about you, Joshua? Ava, Keith, Toby, Andrew, Kieran, Derek? Where are you? You're not voting in on this? Okay. Well, if you don't want to share which one you think will hit first, then just make sure that you've written it down on your paper because it does ask you to make that prediction. And now we're going to talk about it. So let's see. And let's see. You guys might have chatted with me on this because sometimes you don't like to raise your hand, but you will chat. So trying to pull that over here. Can I go back? I'm sorry, I don't know when you wanted me to go back. Somebody wanted me to go back on a slide, but we're going to go forward for now. Okay, so wanted you to think that slide was out of place there. Okay, so I wanted to do a quick little Newton flashback here to remind you what Newton says about objects with unbalanced forces acting on it. So according to Newton, an object that has an unbalanced force on it will accelerate. And if no unbalanced force acts on it, it won't accelerate. It'll stay constant. Okay, so that is what we're thinking about as we're kind of answering this question. So when an object is falling, then it has an unbalanced force of gravity acting on it, right? Gravity is pulling it down to the earth, and gravity is a force. So therefore, it is, that object is being pulled down with an unbalanced force. So according to Newton, it's going to accelerate. And that means change in speed, right? Accelerate means either increase or decrease speed or change directions. But in this case, I think we'd all agree that the object is going to increase in speed, that type of acceleration, when it's falling, when gravity is acting on it. Now, another thing that I want you to keep in mind here is in the real world, as an object is falling, there's air all around us. And so although we can't really see this invisible gas, there are these air particles, and sometimes we can see them when we shine light through them. And as an object is falling, it's colliding with these particles, and that's called air resistance, and it's a frictional force that is actually acting in opposition to gravity. It's opposing the motion of it falling. It's trying to slow it down, if you will. So in your notes, you need to write this down, the word air resistance. Air resistance is a force that opposes motion in an object that's moving. So the more air molecules that an object collides with, the greater the air resistance. Therefore, air resistance is dependent upon the speed of the falling object, and then also on the surface area of the object. So if you were dropping an elephant and a feather off of a building, the elephant is, of course, going to have more mass. So it's going to have more gravity acting on it. As it speeds up, it's going to be encountering air resistance. But the same thing is happening with the feather. Now, the shape of that feather, if you will, I don't have an elephant, but I do have a hammer, and I do have a feather. And you can imagine that as this feather is falling, it's going to catch the air. And actually, let me see if I can angle this a little bit so that you can see the feather and Yogi. It happened pretty quickly, but I'll do it one more time. You can see the feather kind of hitting the wind, and it actually spins a little bit and takes it down. And if I were to, okay, I'm gonna try to angle this so you can see the feather and the hammer being dropped at the same time. It was quick, but the hammer definitely hit the ground first. The feather, sorry, the feather got a lot of air and kind of went down a little more gradually. Yes, Trevor, do you have a question? Or
Oh, no, I just forgot to put it down.
Oh, you just forgot to put it down. Okay. Yes, exactly, Joshua. That's right. So air resistance is why parachutes work too. And absolutely, if you were jumping out of a plane, which I got to do once, and it was so thrilling. And right now, as a matter of fact, couple of days ago, we were supposed to go on a field trip to iFly, and I was going to take you guys to do indoor skydiving. I'm so sorry that didn't happen. But if you were skydiving for real and you hopefully had a parachute, yes, that parachute would catch the air, and then the air resistance trapped under the parachute would pull the parachute back up. And without that air, the parachute wouldn't do you any good, and you would just fall to the ground because of the force of gravity. But because of air resistance, it actually opposes gravity and works in the other way. And I will tell you, when jumping out of a plane, as you're falling, the moment that you deploy the parachute and it comes out, you immediately get jerked up into the air and your direction changes and you accelerate upward. It's pretty cool. All right, going back to our notes here. Okay, so all right. For some reason I have the wrong PowerPoint up now. Sorry about that. And try to share that again. Shoot, did it again. Okay, so where were we? We were learning about air resistance. So you filled the this part out in your notes, and you can even see we were just talking about parachutes here, and you can see a person skydiving, and they are hanging down there, so their weight, their mass, being pulled down by gravity as a force going in the downward direction, and you see an arrow here. The parachute is gathering up air resistance, and that is working in the opposite direction. So that's why there's an arrow pointing upward. This is called a free body diagram, and you're going to have to draw one of these things coming up here in a second. All right, so according to Newton's second law, an object will accelerate if an unbalanced force acts on it. When an object is falling, it's accelerating because there isn't an opposing force large enough to balance the downward force of gravity. So in other words, there's air resistance, but it's not enough to offshoot gravity. So gravity is still an unbalanced force pulling it down. Okay. As an object accelerates, air resistance increases. When an object accelerates enough that the force of air resistance balances the force of gravity, terminal velocity is reached, and the object falls at this constant speed. And that is the fastest that that object can travel. That's called terminal velocity. And I know you have to write that definition down, but I have it on another slide, so don't worry about writing the definition of terminal velocity right now. However, you do need to fill in these three words that you see showing up in orange. So make sure you fill those in your fill in the blanks. That according to Newton's second law, an object will accelerate if an unbalanced force acts on it, and that unbalanced force acting on a falling object is gravity. And so as an object is falling, air resistance is also increasing, and that, as we just made note of, is a force acting in the opposite direction as gravity. So if an object falls for long enough that the air resistance builds up to a point where it actually equals the force of gravity, then the forces will be balanced. And what happens when a force is balanced? Or I should say, when all forces acting on an object are balanced. I shouldn't have gone to the next slide until I asked that question. What happens when all forces acting on an object are balanced? Anybody got that? Newton's first law. What are they going to do if they're balanced? If it's in motion, it's going to stay in motion at a constant speed in a straight line unless acted upon by an unbalanced force, right? So then in the second law, it says what happens when an unbalanced force acts on it. And that means it'll accelerate. But if there isn't an unbalanced force, if all the forces acting on it are balanced, then the object falls with a constant speed. It doesn't speed up. It doesn't stop falling though. It just falls at a constant speed. And that's what terminal velocity is. So you're going to write this down in your notes. That terminal velocity is when the air resistance, which is a drag force or a frictional force, balances out the force of gravity. The object stops accelerating and falls at a constant speed. So the common misconception here is that when an object reaches terminal velocity, it stops moving. It doesn't stop moving. Imagine if you jumped out of an airplane and you were falling through the sky and you didn't have your parachute on, you did have your parachute on, and so therefore air resistance was increasing as you were falling. Eventually, the air resistance would have the same force upward as the gravity force downward. When those forces are balanced, and notice in these pictures on the left, notice air resistance is the upward force. Notice that arrow is smaller than the downward force of the weight, which is gravity. So this person is speeding up because it's an unbalanced force. But in the right-hand side diagram, you should maybe notice that these arrows are equal in size, but opposite in direction. That means these forces are balanced in opposite directions. That doesn't mean the person just stops and never goes down to the ground. You just fall, you continue to fall, but you don't speed up anymore. You fall with a constant speed. That is the fastest you can fall. Not all objects have the same terminal velocity. The feather has a much smaller terminal velocity, a much slower terminal velocity than an elephant would have. So let's look at that situation. Because the feather has less mass and therefore less gravitational force, it's going to reach terminal velocity more quickly and fall at that rate. So what that means is that the air resistance is going to increase as the feather falls. And because the feather's gravity the force isn't very big, it's not going to take as much air resistance for the feather to get those forces to balance out and reach terminal velocity. And once it does, it won't speed up anymore. It'll continue to fall, but it'll fall at a constant rate. Whereas the elephant, being really big, has a lot of mass, it's going to be pulled down to the ground more quickly, more forcefully because of gravity. It's also going to have air resistance acting towards it, probably even more air resistance than the feather. However, it's going to have to fall for a long time before that air resistance is ever great enough to balance out the big force of gravity. So the elephant's going to keep on speeding up. And it would have to fall from a really, really tall place before it would ever reach terminal velocity. Okay, so hopefully you understand then that if there was air resistance, if we really honestly dropped an elephant and a feather off of a tall building, the elephant would hit first and fall quicker. And the reason why is because of air resistance and the fact that the feather will reach terminal velocity more quickly than the elephant. But if we could somehow get rid of air resistance and do this in a vacuum, what would we see? Well, interestingly enough, without air resistance, they would hit the ground at the same time. Now, why is this the case? Well, because Newton's second law says that the acceleration of an object is directly related to the force and inversely related to its mass. So if we rearranged Newton's second law, F equals m times a, to rearrange it to solve for acceleration, the proportion would be force divided by mass. So the bigger the force of gravity, the bigger the mass, that ratio between them would be the same. Let me show you what that actually looks like. Let's say here that an elephant has a mass of 1,000 grams and the mouse just has a mass of 1 kilogram. I should say 1,000 kilograms versus 1 kilogram. So therefore, the elephant's mass is 10 times as great. Its gravity is 10 times that of the mouse. So that makes its force of gravity 10,000 newtons over its mass of 1,000 newtons versus 1/10 of the force of 10 and 1/10 of the mass, 1. And notice that when you divide these, you still get 10. The same acceleration, exactly. And this is what it looks like in animation form. You've got your elephant, you've got a mouse instead of a feather, but the proportion of force divided by mass is equal. And this number is actually a special number. I have rounded it to 10, but it's actually 9.8 meters per second. And we're going to talk about that in the next slide after this. So why does the elephant fall faster than the feather when there is air? And we did talk about that. And the reason why was because air resistance increases with speed, and therefore the feather reaches terminal velocity sooner and falls at a constant speed, which would be much slower than the elephant. And the elephant keeps on speeding up because it doesn't reach terminal velocity as quickly. Okay, so let's answer this quick question. Which of the following is true about the force of gravity? The force of gravity is the same for the feather and the elephant, or the force of gravity is greater for the elephant than the feather, or C, the force of gravity is less for the elephant than the feather. John.
I think it would be B.
You think it would be B? Okay. All right. I agree. It is B. Right. So in the real world, air is almost everywhere. So if an elephant and a feather fell off of a cliff and there was air resistance, the elephant would fall fastest and land before the feather. But in the absence of air, they would fall at the same time. And oh shoot, I don't have enough time. Oh, I'm going to do it anyway. Okay, so I am going to have to change something on our lessons because we have 3 minutes, unfortunately. So what I am going to do is the rest of these notes, I am going to show you this quick video. The rest of the notes that we didn't get to, I am going to do on Thursday. After all, so I'm going to have to change things up. I will make the catapult on a video and post the video so you can build the catapult or not by watching that video, but I'm going to have to finish these notes for you on Thursday, and then we'll be back on track. So let me show you the this experiment that they did in a chamber here. Okay, so.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air.
And it's
kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of...
Okay, I'm going to fast forward to right here where they drop a bowling ball and a feather at the same time in this vacuum chamber where there is no air. And notice that all objects without air fall to the ground at the same rate. The force of gravity is not the same, but they accelerate at the same rate. We'll have to talk about that more on Thursday, but notice, without air, they hit the ground at the same time.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant.
Okay. All right. Hey, guys. So with just like 1 minute to spare, and I have another class coming up, I realized that I bit off more than I could chew today. There was not quite enough time for me to get through all of these notes. Yes, you do need the projectile motion part of the notes to finish your homework on Angry Birds. The notes are posted, but I will on Thursday, instead of doing the catapult building, I will finish these notes on Thursday. They're still going to be due on Friday at the same time, and the homework is still going to be due at the same time. But the building of the launchers, which is optional anyway, I am going to still do. I'm going to record it, and I'll post it on both Edsby and YouTube. And so if you want to, on your own time, watch that video and build a launcher or build your own launcher, we'll use it at next Tuesday's lab. All right. So until then, if you need anything, Edsby, office hours. Hope you guys have a great day. Bye, y'all.